Hey y'all. So what we're going to do today, this is going to be two problems from the Hibbeler book, and this is out of the 14th edition. So we're going to do problem 2.114 and then 115. So they kind of go together, they use the same picture. And I wanted to go over this one because it's talking about projection in the second part, and a lot of students get confused about what projection is. So the first thing we're going to do is we're going to find the angle theta between two cables. So if you can see right here, we've got these two cables. They're attached between A and C and A and B. We want to find this angle between them. We'll do that first. And then after that, we're going to find the magnitude of the projection of the force F1 along cable AC. All right, so when we get to this second part, we'll go over more about what that's actually even asking for. So first, let's find the angle between two cables. Now, the easiest way to do this, or the way that we usually do it in statics, is to use the dot product. So if you went over the dot product, you'll know the dot product is used when you got two vectors, and let's just say we got vector A here, and then we've got vector B, and we've got this angle here. So the generic equation for the dot product is A dot B equals the magnitude of A times magnitude of B cosine theta. So if I can find these two vectors and then their magnitudes, I can get the angle between them. All right, so that's what we're going to use for this first problem. So if you're in statics and it's asking you to find the angle between two cables, this usually is going to be the easiest thing to do. So let's go ahead and let's get our two vectors. Now, we've got these two cables right here, so we need the vectors that represent these cables. So you've got a couple of choices here. You can use the unit vectors for these lines, the position vectors, or the force vectors. Okay, I'm going to go ahead and use, let's see, what should I use here? Let's go ahead and use the force vectors because we're going to need the forces for this part, the second part. So let's go ahead and do that. But you could use any of them. Okay, so let's solve this equation for theta. All right, so we're going to have the arc cosine, and then I need my two vectors, dot product. So let's just say F1 dot F2, and then put that over, F1 times F2. Those are the magnitudes at the bottom. Now remember, you could use the unit vectors and the position vectors also. You get the same thing, all right? Because all of these vectors give you the direction of these lines, and that's what we care about. So let's go ahead and find F1 and F2. All right. To do that, let's write out the coordinate locations for A, C, and B, because that's going to be how we'll find our unit vectors to get our force vectors. So A is right here. Now this is the origin, right? So I need to get my coordinates for A. So this is the x-axis coming out this way. So that means the x-coordinate of A is going to be 2. The y-coordinate, we're going back this way, so that'll be -3, and then we're up 3 meters, so we'll have 3 for z. B is right here. This is on the y-axis. All right, so if it's on the y-axis, the x-coordinate will be 0, y is over 3 in the positive direction, and then z would be 0. And then finally C, which is up here, that'll be -2 because we're going back this way. Then y, it's over this way, so that's going to be a +3. And then finally we're up 4 in that z direction. Okay, so now we've got these coordinates. We can use those to get our forces. All right, so first let's go ahead, let's find the unit vectors first. And then we'll go ahead after that and find the force vectors. So remember, the equation for a unit vector, when we have the coordinates, is going to be the position vector over the magnitude of the position vector. So if I want to find RAB first, all right, then what we're going to do is we're going to take the coordinates of B minus the coordinates of A. And I know that because my force here is pointing towards B. All right, so B is going to go first, and then we subtract A. because it's always the point you're going to minus the point you're leaving from. Okay, so let's just call this RB minus RA, and then with that, we're going to get 0 minus 2, that's your I component, 3 minus negative 3 for J, and then 0 minus 3 for K. And that gives us negative 2I plus 6J minus 3K. All right, and this, checks out with what the picture shows, the signs. All right, so always take a look at your signs, make sure it makes sense with what you have in your picture. All right, so now we've got that, and then let's go ahead and find the magnitude of this. All right, so the magnitude is going to be the square root of the sum of the squares of the components, right? So we're going to have the square root of negative 2 squared plus 6 squared plus negative 3 squared. And put that in your calculator, you get 7 meters. So this means the length of cable AB here is 7 meters long. So that's good, right? All right, so we got that information, and now let's go ahead and find U. So we just put RAB over the magnitude. So that's going to give us negative 2I plus 6J minus 3K over 7. All right, and then, just divide each of those terms by 7, and that gives us negative 0.286I plus 0.857J minus 0.428K. And notice there are no units here on unit vectors. All right, both of these were meters, like the position vector is meters and the magnitude of that is meters, so the meter terms cancel out, so this has no units. All right, so we can use this unit vector in just a second to find our force vector. We'll do that in step 2. So first let's find the unit vector for AC. All right, now again, I'm going from A to C. Okay, so when we do our position vector, we need to do C minus A. All right. So RC, remember these little position vectors? The definition of a position vector is always the origin to the point, and that's what these are. So basically it just gives you the coordinates. If you're wondering why I'm writing RC and then RA, that's why. But essentially what we're doing, we're taking the coordinates and subtracting them. So I need coordinates of C minus coordinates of A. So we get minus 2 minus, or negative 2 minus 2I. 3 minus negative 3 for J, and then 4 minus 3 for K. And that gives us negative 4I plus 6J plus K. And that's meters. Now let's find the magnitude. So square root, sum of the squares. All right, so you get your negative 4 squared plus 6 squared plus 1 squared. And that gives us 7.28 meters. So again, this is like the length of the cable from A to C. So this one here is slightly longer than this one. All right, now let's get our unit vector. So just put this over this. All right, so we get negative 4I plus 6J plus K over 7.28. And then that unit vector, once you put that in the calculator, is 0.549I plus 0.824J plus 0.137K. All right, so we've got our unit vectors. Now again, if I wanted, I could go ahead and find theta right now. I could use the position vectors to do that, or these unit vectors. Okay, you could use any of those. We could also use the force vectors. I'm going to go ahead and use the force vectors just because I need the force vectors for later anyways. So, but you could use these other sets of vectors also. Okay, so let's do the next step. And let's find F, force vectors. Okay, so let's start with AB. So FAB, remember how you find a force vector. You're going to take the magnitude of the force times its unit vector. So for AB, my magnitude is given as 70. All right, you might want to call this F1, I guess. They call it F1 on the picture. So we got 70, and we're going to multiply that by the unit vector that represents line AB, so UAB. Okay, so we got 70 times this unit vector right here. And this gives us our Cartesian form of the force. All right. So now we'll just multiply through by 70 on each of these. So it's negative 20.02I plus 59.99J minus 29.96K. So this is our force vector. All right, and units here would be newtons. And then we'll do the same thing for F2. Now, what's the magnitude for F2? Well, it was given as 40, right? That was the magnitude. So we're going to take 40 and we're going to multiply it by the unit vector along AC. So that was our UAC. All right, so we got 40 and then UAC is right here. So let's write that out. Like that. And then once you put that in your calculator, you're going to get negative 21.98I plus 32.97J plus 54.9K. That's in newtons. So this is our force F2 in Cartesian vector form. So now that I've got these forces, I can go ahead and find theta. All right, so theta, remember, is going to be the arc cosine of F1 dotted with F2 over the product of those magnitudes. Okay, so first let's focus in on finding the dot product. So let's do F1 dotted with F2. So we're going to take this vector and then this vector, and we're going to dot them together. Well, let's hope I have room here. I'm going to be getting small. There we go. Okay. Now remember how we do the dot product. All right. Because a lot of people haven't seen the dot product when they get to this section. So the dot product, what you're going to do is you're going to multiply the like components, and then you're going to add up these products. So I'm going to multiply these two together, the two I terms multiply together, and then I'm going to add to that the product of the J terms. So these two will multiply together, and then finally add to that the product of the Z terms. Okay, so you got to find those terms and then add them up. Okay, so this is going to be negative 20.02 times negative 21.98 plus 59.9 times 32.97 plus negative 29.96 times 54.9. So then you do that calculation. That is going to give you your dot product. All right, let me get another piece of paper here. So once you end up calculating all of that, we end up getting 2,253.43. All right. Now we've got this. Let's go ahead and plug it into our theta equation. Okay, so the dot product was 2253.43, and the bottom, we need the magnitudes, right? I need F1 and F2. The magnitudes, do we need to calculate that? Do I need to go through and calculate the magnitudes of these? No, I don't, and we know why? Because they were given in the problem, right? Remember in this expression right here, this number 40 is the magnitude, same as 70. That's already the magnitude, it's already given to you. So we don't need to recalculate it. We just need to do 70 times 40 here. And then you can put that in your calculator and get theta. All right, make sure your calculator is set to degrees. And if you do that, you get 36.41 degrees. All right, so this would be the angle between these two cables, right? So that angle is at 36.41 degrees. And that's how you do it. All right. And again, remember, like I said, if you just wanted to find the angle, if you didn't have this second part of the problem coming up like we do here, you could literally just use these position vectors in here, right? You could use the dot product of the two position vectors and then put it over the product of the magnitudes of the position vectors, and it would be a lot shorter. All right, I went ahead and found the force vectors just so we could go through finding the unit vectors, force vectors, and all of that, because we need some of that on our next part of the problem. Okay, so this was part 1, so here's part 2, and let's revisit part 2. So this says to find the magnitude of the projection of the force F1 along cable AC. Okay, well, when I teach this section, a lot of students read that question and they don't even really know what that is asking for. Okay, so projection, I always tell everybody, is just a fancy word for parallel component. That's essentially what that is. So what it's wanting is it wants the magnitude of the parallel component of F1 along cable AC. Okay, so that is all it is wanting. So essentially, if we've got F1 right here, it wants to know what component of F1 lies right here along this line. That's what it's asking for, is the parallel component. Okay, so when you see that, you should think dot product, because the dot product deals with parallel components. Okay, cross product, on the other hand, deals with perpendicular components, right? So anytime you want a projection, which is a parallel component, we want the dot product. Okay, so let's go through and do the dot product here to get our projection. All right, now the way we're going to do this is, let's write it out. So the notation I use is, I'm going to say F1 parallel to AC. Okay, that's going to be our projected component. All right, notice there's no bar up here, because remember, when you do the dot product, you get a scalar, you do not get a vector. So no bar up here. And the equation we're going to use is basically going to be the unit vector of the line we are looking at, which is AC here, and we're going to dot that with the force vector F1. Okay, so this is going to give me the projected component. All right, so let's go ahead and plug in our numbers. So we already found the unit vector for AC, and we already found F1. We just need to dot them together. So UAC was right here. So let's put that in here. All right, so there's UAC, and then we're going to dot it with F1. F1 is right here. Okay, and then now we do the dot product. So remember, we multiply the like terms and then add up those products, right? So we're going to have negative 0.549 times negative 20.02 plus 0.824 times 59.99 plus 0.137 times negative 29.96. And then we add these up. All right, so that value is going to give you 56.32 newtons. And this would be the answer for that projection question. Okay, so 56.32 newtons is the projected component of F1 along cable AC. All right, now notice when you do this, you get positive or negative. Okay, so this is positive. So positive indicates that the projected component is in the same direction as the unit vector AC. Okay, so that's what the sign indicates. So if we would have gotten a negative here, that would imply that it's in a different direction. It's going in the opposite direction. And we could see that by looking at the picture, right? So if I'm finding this parallel component right here, like we drew in the pink, it's going in the same direction as that line from A to C, okay? Because our unit vector, when we calculated UAC, we said we were going from A to C, all right? And that's how you would find the projected component. So remember, a projected component is just the parallel component. That's all it's wanting. Okay, and we can find that using the dot product. Okay, now one more thing I want to show you. It asks for the magnitude. Sometimes it'll ask for the vector form. So if it asks you for the vector form of the projected component, all you need to do is take this magnitude you got, so 56.32, and then multiply it by the unit vector of the line the component's acting on. So that's the UAC. All right, and then that will give you the vector form. All right, I don't have this calculated, but that's how you would find it. All right, so that gives you the vector form. And then last thing I want to show y'all is just a quick way to do this, given the information we already found. So we already found this angle of 36.41, right? We found that. So let's look at this picture over here. So this angle right here was 36.41 degrees. Okay, well, let's think about what we could do here. I know this angle here between F1 and this parallel component. Now, if you think about it, if you were to break up F1 into components like this, could we not also say that this component right here is F1, which is 70 times cosine 36.41? We could, right? So if you've already found the angle, it's real easy to find that parallel component or the projection along that line. Okay, so we could also do that. So we could say 70 times cosine 36.41 degrees, and then that equals basically the same thing. So you're going to get that 56.3 newtons. Okay, so if you were given a problem like this where it asks for both of these things, the angle and the projection, this is a quick and easy way to get the projection once you've already found this angle. Okay, so a lot of the times on tests though, you'll have one or the other, right? You won't have both. So if you haven't already found the angle, this is the way you'd want to go about finding the parallel component or the projection. All right, so hopefully that helped a little bit. Just a quick example of projection. All right, so I will see y'all next time. Y'all have a good rest of the day.